All right, welcome back, class. Today we discussed what a series parallel combination circuit was. So in the previous chapters, chapter 4, we discussed what a series circuit, meaning there was only one path for current to travel. In a parallel circuit, we had multiple branches, and then today we're going to talk about a series parallel or combination circuit where you have some series parts to the circuit and some in parallel. So if we look just by definition, series means one path of travel or one path for current to flow. So if we look at this voltage source here, as we leave the voltage source, has to go through this resistor, come down through here, and there's only one possible path that the current could travel to get back to the voltage source. This also being a series circuit, notice when we leave the voltage source, we pass through this resistor, comes back down, and even though this makes a little different shape, there's still only one possible path for the current to travel to get back to the source. So both of these are series circuits. And we know from the formula that a series circuit total resistance is just simply the sum of all the resistors in there. And depending on however many you have, this goes out as far as you need to an nth number of resistors. A parallel circuit. Notice in a parallel circuit we have branches, multiple branches. So as the power leaves here, I'll draw it top. When it gets to this node, refer to this as a node right here. Once it gets here, the current has two possibilities. It can travel down through this resistor, or it can continue on and travel through this resistor. I now have two paths or multiple paths for the current to travel, and then they will eventually get back to this node and recombine and finish their trip. But there's no series in this. Once it comes out, it goes through two different resistors, and that makes a parallel path. If we look at this one, we come up here, we get to this node, and we can go through that resistor. We can come down, get to a second node, go through this resistor, or we can go through this resistor, and then all of these will recombine back to get to the voltage source, this being a parallel circuit. And we know that the total resistance for a parallel circuit is equivalent to the 1 over the reciprocal of each of the values. Again, however many are in that sequence, so we could go from to R to the nth one, depending on how many are. In this case, we have 3, so it would be 1 over the reciprocal of R1 plus the reciprocal of R2 plus the reciprocal of R3. This would be the total resistance for a parallel circuit. Today, we discussed series parallel combinations. So if we look at this particular drawing, when we leave the voltage source, we go through this resistor, but when we get to here, we wound up at this node and we can branch out to multiple directions. We can go this way, we can go this way, then they'll recombine back and go up through there. So in this case, this series is in, this resistor is in series with these two resistors that are in parallel. So we have a series portion of it and we have a parallel portion. So it has the combination of the two. The way we would write that out, I'll find a good marker. This is all we got. If this is R1, let's say this is R2, and this is R3. So R1 is in series, so we're going to add them together to this parallel circuit of R2 and R3. So we're going to put them in parentheses because these two are together. So R2 in parallel with R3. So this is going to be the total resistance is going to be R1 in series with the parallel circuit from R2 and R3. So this is a combination circuit. If we look at this example here, let's call this R1, R2, R3, R4. If we trace our possible path out, current would flow here, get to this node, branch out, and go down through two different sides. So we can go this direction, or we can go in this direction. But notice as we're passing through here, these two are in series with one another. These two are in series with one another, but the two paths are in parallel with each other. And then once they get back, they recombine and return to the voltage source. So if we write this one out as the example, the total resistance would be equal to the parallel of R1 in parallel with R3. Excuse me. That's in series. R1 and R3 are in series. So the series of R1 and R3 in parallel with the series of R2 and R4. Whenever you see a plus sign, that means it's in series. Whenever you see the parallel sign, that means it's in parallel. So we have these two combination circuits here. R1 in series with the parallel of R2 and 3, and then we have R1 and 3 series circuit in parallel with the series of R2 and R4. So in these combination circuits, it's not just as simple as using one of these formulas. We have to actually pull the branches apart and see, we have to make what's called an equivalent circuit. And that's what we're going to get into today, is we're going to discuss how to break this down into the equivalent circuit so we can get the total resistance. So